Hi all, this is Claudio from expertfe.com with a new series called ANSYS FEA from Basics to Advanced. A short reminder about our YouTube channel with more than 500 video simulations, our website expertfe.com, and of course for more advanced simulations you feel free to join our Patreon account for lots of benefits. Let's cut straight to the topic. Today we are going to drag and drop a static structure simulation and follow the natural steps in this simulation. For example, the first cell that is editable engineering data deals with the materials. The default material from here is structural steel. Let's click this row of books and add from general materials also aluminum alloy. Plus, we click the plus sign here, we uncheck the button engineering data sources, and we have here the aluminum and structural steel defined in a let's say linear manner. We don't have at this moment treated the region above the yield limit. We do not have plasticity defined. It will be the case for the next episodes. For the geometry, let's double click the next cell. It will open the discovery module, which is based on the formal space claim geometry modeler. So in a few seconds we will draw a simple beam and we will apply the simplest load that exists in the strength of materials. Hence, afterwards we will compare the results from FEA with theoretical values. So discovery is being open now. While time passes by, let's give a small reminder about how this case will be played. It will be a simple extension. This is the force. Here we'll have somewhere there will be an area, and we will need to find the stress, which is force divided by area, then the displacement, the axial displacement, which we will call it delta L, and the formula for delta L you might remember from strength of materials: force multiplied with length over Young's modulus multiplied with area. So we are positioned here in a sketch. Let's just click the rectangle button. We'll select a point, and let's stop where is written 10 by 10. Alright, click 10 by 10. Now we need to get out from the sketch. We click on return to 3D. It says pull here. Let's select the surface to be pulled. And let's write from the keyboard, for example, 150 millimeters. We do have this beam with the side 10 millimeters. At this moment, we can close the geometry modeler. The next cell that can be modified is model. Let's double click. Now ANSYS workbench opens the so-called mechanical window, in which we will do the pre-processing, the solving, and the post-processing. Everything in one window. We can see here the mechanical window. In background, the geometry is being imported. And the model tree will be populated shortly. It takes a little time because in background it also opens the discovery module that we just closed 1 minute ago. So this is the beam. Come on, software. All right. So let's follow what we have in the model tree. We have the geometry import, which is not editable. In the geometry, we do have the only part. We can rename it beam, for example. What's important here, we do have the material defined structure steel at this moment. We will also replace it for aluminum, just to make a comparison, let's say. So the next step, we do have the materials defined. Here it's the fatigue part, let's say. But we're interested here in the isotropic elasticity definition of both materials. A global coordinate system, where we initially positioned the sketch. And here is the mesh. Let's just right click generate mesh. For such a simple geometry, hexahedron elements will be generated here. Let's apply the load. The simplest scenario is to fix one face, then to pull the other face with a force. Force, click the face, apply, and let's say 20,000 newtons. The next step, we can scope for deformation solution. Strain equivalent. Also, let's search for the plastic strain. And regarding the stress, equivalent for misses. At this moment, let's save the project. So it's called ANSYS FEA from basics to advanced lessons. And this is lesson 1. Here we can go and say lesson 1. For engineering data, F2 to rename. Just steel, let's write here. And let's solve. We expect the solving to take a few seconds because of the very low node count. So we have a pretty coarse mesh. So the node count is 621 nodes. So the total deformation and the directional deformation, they seem to differ, but the problem is that we need to scope the directional deformation about the important axis. We applied the force about the z-axis. So let's change here to z-axis. Right-click, retrieve this result. And it's almost the same as with the total deformation. Elastic strain gives us, it will give us an overview if we are going to exceed or not the yield limit, if we are going to enter the plastic realm. And because we have 0 here in the plastic strain, it means that we didn't exceed the elastic limit. Maybe you remember for steel there is a certain value, let's say, the limit of proportionality, and epsilon for 0.2% means that we do have a limit of 0.002. Either you make it millimeter or meter over meter. Please compare this value with this value, and you can see that we're not exactly near the yield limit. Yes, we're not touching this limit and we're not above it, so we're in the elastic realm, we're not in the plastic realm. This is why we do have 0 here. And regarding the stress, let's see, we don't evaluate the stress here because it's maximum at the point of fixation. Instead, we are going to scope the stress here and here. Now, a little, let's do some calculations. We know that the formula for stress is this one. The force is 20,000 newtons over, if we have 10 millimeter per side, yeah, we have 10 millimeters square, because it is a square after all. This means the measurement unit is megapascals or Newton per square millimeter. And we have 20,000 over 100. We can reduce this, and the value is, as seen in FEA, 200 megapascals, which is exactly, yeah, these values. So we do have now a confidence that FEA matches the theoretical calculations. Now, regarding the directional deformation, let's also apply the formula that I have just mentioned a few minutes ago. And the formula said force multiplied by total length over Young modulus multiplied with area. So this gives 20,000 newtons multiplied with 150 millimeters the total length. The Young modulus is around 200,000 megapascals, which can be written as Newton over square millimeters. So this is the Young modulus, yes, this one and this one, multiplied with the area, which we already know it's 100 square millimeters. Let's reduce what we can, Newton and square millimeters. And if possible, let's also get rid of 4 zeros from here, 4 zeros from here. And let's wait a little, okay? Let's not become confusing. So we have 2 multiplied with 150 over 20 multiplied with 100. millimeter. This is the only measurement unit that remained. So we have 300 over 2000 millimeter, which is exactly 0.15 millimeters. Let's confirm. Yes, exactly, and closest to this value. Alright, we have these values. Now let's replace the material with aluminum and let's remake the simulation. Solve. And we will see what changes now. We expect the stress to remain the same because the stress is a function of force and area. It's not related to the material. So, as I said, the stress is the same because it respects sigma equals F over A, which is unchanged to 100 megapascals. What changed is the directional deformation, 0.42. Let's also calculate it theoretically. So F multiplied with L over E or multiplied with A, 20,000 newtons multiplied with 150 millimeters. We know that the Young modulus for aluminum is around 70,000 megapascals, but we can always see it here. 71,000. So let's go here. 71,000 megapascals, which is Newton over square millimeters, multiplied with area, which is 100 square millimeters. Let's reduce what we can. We do have here 3 zeros and 3 zeros, and I would like to cut 1 zero from here and 1 zero from here and get rid of this. So delta L, the only measurement unit is millimeter. So we have 2 multiplied with 15 over 71, which is 30 over 71, and the result is 30 over 71, 0.42. Which is almost exactly this result. So at this moment we have seen the basics in FEA. This is the simplest case of tension, and we have seen a comparison between the simplest cases in FEA and in strength of materials. That is all. I will be waiting for you for the next similar lesson. So, bye-bye.